In this session, we are going to be discussing about chemical kinetics. When we hear this term, kinetics, that means we are going to be discussing about the rates or reaction rates. In general, we can divide the rates between the average rate and the instantaneous rate. Suppose we have a reaction of 2A plus B forming 3C. If we draw a plot of time or reaction time for the x-axis and the amount of substance as the y-axis, for the reactants, it's going to go from a certain amount going down until it reaches a plateau. For instance, this is for concentration of A, normally in molarity, and this one, say, for the concentration of B, which is also normally in molarity. While the product, at the beginning, there is no product, and then it is formed after a while and also reaches a plateau. If we take only 2 points among any of this plot, if we take 2 different points, so 1 and 2, we can find the average rate. So average rate by taking the delta of the molarity of, for instance, C from the second state and the first state divided with the delta T. This is what we call the average rate. However, for the instantaneous rate, what we take is the tangent line. Therefore, the rate is going to be a very small difference between the concentration of C divided by a very small difference in the time. And in this case, if we take an instantaneous rate, we have to specify also to which T. Say we take a tangent line that is colored in orange, so something like this. Now this tangent line is instantaneous rate, which is the first derivation of concentration over T, approaching T equal to 2. The reaction rate that we are going to be discussing is actually the initial rate that approaches T equal to 0. It's actually an instantaneous rate as well, so this one, but approaches T to 0 because in the beginning we do not have any product yet to intervene with the collisions of the reactants to form the products. And therefore, generally, initial rate is the optimum or the maximum rate for a reaction. Now, say again that we have this imaginary reaction to help us understand the chemical kinetics of 2A plus B becoming 3C. We define the rate as half of the subtraction of A over T, also minus of subtraction or consumption of B over T, and plus 1/3 formation of C over T. Now in this case, for reactants, we always use the negative sign as the rate has to be positive, while the reactants, as we can tell from the plot in the previous part, it will go down. However, for product, we use positive because we are forming products and their number increases over time. Note that here we can define the actual overall reaction rate. However, we can also define how fast A is being consumed, so the rate of reactant consumption, either A or B, is the same thing. And we can also define the rate of product formation. Normally, R has the unit of molar over the unit of time. So molar over second, molar over minute. And for reactions like nuclear chemistry, we can also use molar over year. However, in the case where we have all gaseous reaction, we can also use pressure instead of concentration in molarity. So sometimes we also have the unit of R being atm over the unit of time.